Swayam Prabha. Digital India. Educated India.
Today we will discuss about pipelining and parallel processing for low power applications. The recap of the last classes, we discussed about linear phase FIR filter in length and then how to build it, that is what we have seen in the last class. In today's class, how we can use the architecture, that is pipeline and parallel architecture, to build a FIR filter for low power applications. So, when I talk about the low power, in this case we will be considering the capacitive load power consumption, which is given by PL is equal to CL into VCC squared into F naught into NSW. So, we say that the power is proportional to we say the frequency and square of voltage, what we call it. So, we can, if we reduce the voltage, we know that the power consumption is going to come drastically, but for speed we have to increase our frequency. So, we have seen that we can use the architecture for speeding up our computation using pipeline and parallel. So, the frequency is going to be increased, but in this case we will see that how we can use the thing by reducing our power consumption, by reducing our operating voltage. So, here we will give it PL as a capacitive load power consumption and VCC is our supply voltage and F naught is our output signal frequency and CL we call it as external load capacitance basically, and NSW will be total number of outputs switching. So, if we assume 1 bit what we are transmitting, so it becomes N is equal to 1. So, switching load will be 1 in this case. So, if we have more number of bits, that also will be contributing to our power consumption. So, we will see what is the basic idea of pipelining, which I have already discussed, that is we took either a car assembly, in this case example is given Henry Ford in 1908. In 1914 what they were taking time is 3 minutes, what was the every car was coming out. So, latency in that case we say was 93 minutes basically. The maximum time what was taking, although they were able to achieve 3 minutes, but as you can see 93 minutes was the latency between two cars because one of them was taking more time. So, what we call that example, we took the water pipe in the last class. So, we will be seeing that the pipe of the length of the water pipe is less, then our latency is going to be less, but if it is long then we know that it is going to have a maximum latency, we call it as critical path. So, further increase the clock speed or sampling speed to or reduce the power consumption for the same speed in a DSP system. So, for the parallel processing we will have multiple outputs are computed in parallel in a clock period. The effective sampling speed is increased by the level or parallelism if we want to increase the speed, or we can reduce the power consumption. So, why do we need pipelining and parallelism? One is to reduce our critical path, that is the longest path delay, and increase the clock speed or sample speed what we are putting it, or achieve a reduced power consumption. Same thing with parallel processing, not reduce the critical path here, not increase the clock speed, but increase sample speed, and then we can use it for reduced power consumption. So, we will see the data flow in parallel and pipeline structure, how it is going to be implemented. So, we say that we have 4 processors here, P1, P2, P3, P4. if there is no data dependencies, we know that all the 4 processors will be working on different data sets. So, if we have the same number of processors in pipeline processing, so we say that each processor has to wait for the previous data to be finished, computation to be finished, and then it should be coming into the next stage. So, each processor you will be seeing that the latency of this P4 processor is it has to wait for 4 clock cycles till it can operate. So, once all the data have been filled, then they can work in parallel. So, that is what the latency of the pipeline, whereas in the parallel processing all of them there should not be any dependency between the data in this case. So, when we say that how it is going to have this thing data dependence, we say that in parallel processing requires no data dependence between the processors, then only they can run in parallel. So, as you are seeing it, the data flow in P1 processor is going to go in horizontal way, same thing with respect to rest of the processor. Whereas, in the case of pipeline, we said there is the data dependency between the 2 processors. So, P2 is waiting the data from P1, the same way P3 will wait from P2 and then P4 will be waiting from P3. So, this is how the data will be, if they are dependent, then the flow is going to be in this fashion. So, coming to the usage of pipeline processing, how we can do the thing? We can do by inserting latches or registers between combinational logic circuits. So, that way we will be reducing the critical path, or it can be shortened. So, the consequence of introducing this is will be reducing the clock cycle time and increase the clock frequency. So, it is suitable for DSP applications that have we call it as infinity long data stream. So, we are assuming that input data is coming continuously. So, we have to operate on that. So, method to incorporate this pipelining, how we are going to do it, we will see it in a while, using the cut set and then do the retiming of the circuits. So, we will define the cut set, we call that as a set of edges of a graph. If these edges are removed from the original graph, the remaining graph will become 2 separate graphs. That is, there are no dependence between the 2 graphs, they have to become independent, then only we call that as a cut set. Usually we apply feed forward cut set in our filter. So, in this case we call feed forward because data move in the forward direction and all the edges of the cut set. So, there will not be any feed backward data flow. So, only we consider if there is a feed forward data, then we call that cut set as a feed forward cut set. The other one is retiming. So, how we are going to see the retiming of an algorithm is readjusted while keeping the partial ordering of execution unchanged, so that the results are correct. So, we will see that how we will be doing that. So, as an example, we will take that this is the data flow graph what we have it. So, data is moving from A1, A2, A4 and then A6 is the last thing, or it can flow in this direction. So, we say that D means there is a delay in this data path. So, what will be the longest delay, that is what we see we have to see in this graph, or we call it as the critical path. Since there is a delay, so we will assume that it will be going into this register, it can be a register or a so that it is going to hold the data and then in the next clock cycle it will be going into this point. So, here we will be seeing that from A3 the data has to flow to A5 and then to A4 and then to A6. This is the longest path in this. So, which we call it as it is going to take 4 clock cycle or 4 unit time to get the data from one node to the last node in this case. So, we said that we will put a cut set basically. So, I can cut the graph into 2 pieces in this way, and then we said we are going to introduce delay units wherever we have put the cut set. So, or a shift register, one of the thing what we will be using it. As we can see that we have cut this into 2 parts this way, but we have forgotten to put a delay unit here. So, that is how it says this is an error basically. So, how if we cut this properly and then put all the delay units in the cut set, then what happens to our critical path, what we will see it. So, we say that from A3 to A4 I have a delay path, and then from A4 to A6 it is direct, and then what we have is from the delay unit, if I take that the data is moving, it has to move to A4 and then A6. So, that way it takes 2 clock units to reach the maximum delay in this circuit or in the data flow graph. So, what is it? So, some of the concept what we will see, how we will be representing our pipelining and parallel concept is represented. In the pipelining, we introduce pipelining latches along the data path. So, this is the original circuits, x of n is the input, and then this is one of the a of n is the coefficient, b of n minus 1 can be the other coefficient. So, y of n is going to have it as a of n into x of n plus your b of n minus into x of n basically. So, this is my y of n. When I say that the critical path is going in this case is 2 adders. So, it has to pass through them to get my y of n. So, I want in a single clock cycle my y of n has to come out. Then what I do is I cut this u line into 2 parts and introduced a delay line. So, I am increasing the hardware. So, x of n is this, it will be added in 1 clock cycle, and this is going to be latched here, and in the next clock cycle I will be adding with whatever data coming from here, and the output in the current state is going to be y of n minus 1, and then in the next clock cycle I will be getting the y of n. So, I will have compared to previous structure I will be getting 1 delay output, initial output, after that it is going to come continuously. When we talk about the parallel processing, so we will be duplicating the hardware. So, here we have duplicated 2 units basically. Then what happens to the input? It has to be x of 2k to the 1 of the stage, for the other one x of 2k plus 1. So, here even the coefficients as you will be seeing it, it becomes a of 2k and b of 2k. So, k will be varying from 0 to n minus 1, in this case only 2 what we have it. So, the other input to the second structure is a of 2k plus 1 and then b of 2k plus 1. So, coming to the thing, when we use FIR filter, we will consider as a 3-tap FIR filter. So, if we use the direct form structure, as you are seeing that I am talking about the structure, even the structure is going to matter when we are designing our circuit. So, here we have used the direct form. In that case, what is the equation for my FIR filter? Y of n is nothing but a into x of n plus b into x of n minus 1 plus c into x of n minus 2. So, we say that the sample period T sample should be greater than or equal to T m, that is the multiplier, plus the longest path in this is going to be from here to here, which is going to incorporate 2 adders. So, my sample period has to be T m plus 2 T a. When I talk about the sampling frequency, should be less than or equal to 1 divided by T m plus 2 T a. So, depending on the time it is going to take to multiply and then add will decide my sampling frequency for this 3 tap FIR filter. So, the coefficients what we have assumed is A, B and then C. So, how will I get my y of n? What is shown here, x of n is the input and these are the delay lines x of n minus 1 and then x of n minus 2. So, as the equation suggests here, y of n is equal to a into x of n and b into x of n minus 1 plus c into x of n minus 2. So, that is what my 3 tap FIR filter. When I consider the sampling frequency, what should be for this structure. So, if I talk about the sampling period, T sample should be greater than or equal to the time taken to do multiplication, and because the longest or the critical path delay what we call it here is 2 adders what it is included, 1 multiplier and then 2 adder. So, it becomes Tm plus 2 times time for addition. So, the sampling rate is going to be less than or equal to 1 by Tm plus 2 Ta. So, we will see how we will avoid this. One of the thing is, as we said, we can have a cut set in the, because as you are seeing in the structure all of them in the feed forward path, the flow what it is going. So, I can have a cut set. So, we said that it is taking 2 clock cycle to add, whether I can reduce it to 1 clock cycle. Then what I am going to do is I am going to put a cut set here as you are seeing in the blue line in the forward path, that is what it is shown here. Then I have to introduce 2 delays in the path because I have cut 2 lines here. So, there will be addition of delays in this case. Now, you will be seeing the longest path in this case is going to be, so 1 multiplication and 1 addition. So, we will come back what we are going to define what is my longest path, okay. And from here to here also it is going to take 1 clock cycle, and from this delay to my output is going to have 1 clock cycle. So, we make this structure as first unit and the second unit what we have it. So, what happens to the output? That is what it says is critical path from 2a plus Tm, which is changed to Ta plus Tm. So, the clock we will see the what will be the output at 0, the input to this is x of 0, then node 1 what we call it, what is going to happen in this clock cycle is it will be multiplying a into x of 0 and then it will take b into x of minus 1 in this case. So, in the next clock cycle, so you will be seeing that x of 1 will be the input to this unit, and then the thing is going to be node 1, it is going to compute a into x of 1 plus b into x of 0. So, in node 2, because this has moved to the next clock cycle, so it will be a into x of 0 previous one plus b into x of minus 1, and in node 3 what we call it is here, which is going to be c x of minus 2, and this will be my y 0. And same way you will be seeing that in the third clock cycle, so the all the units become full, then y 2 will be my output, which is completely correct. So, compared to the previous one, you can draw this sketch for the one which did not have the cut set. So, output will be start coming from here y 0, y 1, y 2, y 3, but in the this thing pipeline case, in this case since we have put only one cut set, the delay is going to be 1 clock cycle. So, we will not be getting anything here, it is irrelevant or it is garbage what we will have it. So, output starts coming from here. We will see effect of pipelining. What are the drawbacks? We will be increasing the delay elements, number of delay elements, what we call it as registers or latches in the critical path. This is a hardware addition what we have to provide. This causes increase in latency. Then what we say is the clock period limitation, we will see it. So, the critical path may be between an input and a latch we call it, a latch and an output, or between two latches on input and an output. So, this we call it as the critical path. So, this is how we measure how many multipliers or accumulators or how many hardware is in between these two things. That will be the maximum critical path what I have to consider. So, we say pipelining latches can only be placed across any feed forward cut set of the graph. This we will be specifying every time, and then we have to go through the thing. Next one is, as I was talking about the structure, can we have a transposition theorem incorporated in the signal flow graph? That is, what we are going to do is reversing the direction of all edges in a SFG signal flow graph and interchanging the input and then output ports, preserve the functionality of the system. So, we say that x of n is the input, y of n is the output, this is in the feed forward what we have it. So, this delay can be represented as a d, or in the z domain we will call it as z minus 1 is going to be the delay. So, each node will be representing my this as an adder and this as a multiplier. So, now what we are going to do is, my output I will be changing it as an input and then input as an output, and all the direction are going to be reversed basically. That is what the transposition theorem says. So, as you see the thing, y of n, and then we will be keeping ABC as it is. So, this has got changed. Now, what is the thing is going to happen? So, we will incorporate in our data flow graph here from the signal flow graph. We call that as a direct form 2 structure. We call that as a data broadcast structure, and in this case you will be seeing that the critical path without adding any delay elements, it has become Tm plus Ta. We will see it in a while how it is going to be. So, to have the understanding correctly, what we have done from the previous thing, we have reversed the implementation of this graph actually, so that we are not comfortable going from right to left. So, we will put it back as a forward path itself. So, you will be seeing that x of n is going to be broadcast to all the 3 multipliers. Here it is C, here it is B, and then A, and then we have a delay element already present in the original one. This is the original. Now, you say see the thing, the critical path in this case is going to be 1 multiplier and 1 adder. This is from input to output, and then from input to latch is also 1 unit, and then here also it is going to be input to latch is here only have a 1 multiplier delay. Okay. So, the maximum that is critical path is 1 multiplier and 1 adder. So, you can see that the structure, if you choose it properly, I need not have to have any cut set or any pipelining introduced in some of the graphs that one has to consider. Now, we will say that all of us know that multiplier is going to take longer time compared to my adder. So, as an example, we call this as a fine grain pipelining. So, let Tm is equal to 10 unit time and adder takes 2 unit time, and the desired clock period what we want is 6 unit of time. So, how we can achieve, because multiplier is going to 10 units plus 2 units will be my longest path in the broadcast section if I am computing it, but my clock period has to be 6 unit. Then what we do is we can bifurcate our multiplier into 2 smaller units with processing time of 6 and 4 units. So, you will be seeing that one multiplier M1 is going to take 6 units, and then M2 multiplier will take 4 units. So, we are doing a cut set here in the forward path and then put a delay element in all the 3 legs of my filter, and then we will be seeing that from anywhere to anywhere, that is input to my this latch is 6 units, in all the cases, and from here you will be seeing this latch to this latch is only 4 units, and the whatever shown in the blue will be the my critical paths basically. From this latch to this latch it has one multiplier and one adder. So, which will be taking 6 units of time, and from here to here also. So, this we call it as fine grain parallelism or sorry pipelining. So, the next one we will see that parallel processing how we are going to work on. We say they are dual basically, and if a computation can be pipelined, it can also be processed in parallel. That is what we say. So, how we are going to do this? We say convert a single input single output. SISO is my single input single output, that is what x of n to does. System into a multiple input multiple output, we call it as MIMO system via parallelism. So, you will have a scene here input is x of 3k, x of 3k plus 1 and x of 3k plus 2. You will be wondering what is it. Initially we took example parallel for 2 parallel systems. Here we are assume 3 parallel systems. So, you will be seeing that your x of n will be changed as x of 3k in this case, and y will also be y of 3k plus 1 and 3k plus 2. So, this is 3 parallel system. Then what happens to my input and output representation? We have original what we have is y of n is a into x of n plus b into x of n minus 1 plus c into x of n minus 2. When I pass this in 3 parallel section, what will be my output is y of 3k, 3k plus 1 and 3k plus 2. How the inputs have to be, you will be seeing it. So, I will be replacing n with 3k, a into x of 3k plus b into x of 3k minus 1 plus c into x of 3k minus 2. So, in the next case 3k plus 1, what we will be adding with respect to n is 3k plus 1. So, if you substitute that 3k plus 1 and then 3k plus 1 minus 1 will become 3k, x of 3k in this case, and then in the next case c into x of 3k minus 1. So, you will be seeing even y of 3k plus 2 will be represented in this way. Then what happens? We call time taken for iteration is equivalent to t sample, what we call it. Here in this case it becomes 1 by L into t clock. So, which is greater than or equal to, because number of parallel section I have assumed is in 3 here. So, which becomes 1 by 3 into 1 multiplier plus 2 adder, because I have not put any pipelining here. So, adder delay is going to be 2 units in this case. So, what happens to 3 tap FIR filter, how I will be representing it in the direct form 2 as you will be seeing it. So, if we use the direct form 2, what is the thing? So, this is the output what I want, y of 3k, 3k plus 1 and 3k plus 2, and we will consider y of 3k plus 1, rest of it you can work it out. So, we will see that how we are going to get a into 3 of a into x of 3k plus 1 what I wanted the first output. So, you will be seeing that x of 3k plus 1 is coming here, and then which is fed to my here this multiplier which is a into x of 3k plus 1. So, which goes into the adder. So, what the next one what I want is b into x of 3k. So, you will be seeing b is here, and then x of 3k is the thing which is coming here, which is going to be multiplied with your b x of 3k. So, which gets added. So, what is the last one what I want it? C into x of 3k minus 1 what I want in this case. So, how we are going to get the thing? So, what we will do is I can take x of 3k plus 2, because when I introduce the delay line in this, because this is the 3 parallel structure what we have taken the thing. So, delay is going to be 3 units. So, this becomes x of 3k plus 2 minus 3. So, which is with 1 delay. So, it is going to be x of 3k minus 1 this input, which is going to be multiplied with C. So, all of them get added and then we will be getting y of 3k plus 1. So, you can check the rest of them whether you are going to get this equation correctly with the structure or not. So, thank you for hearing this lecture.